Well, first I would like to thank the organizer and Mitio Inukuti for their invitation to talk about electron resonances and dielectric hysteresis. This work was done within the group of the Medical Research Council of Canada. Well, actually, this has changed recently. It's now called the Canadian Institute of Health Research in the Radiation Sciences. And much of the work I'm going to show was performed by Marc Michaud from my group. Now, I guess like everybody else, I should mention that I am not a legitimate or illegitimate son of FANO, but very early in my career, I became acquainted with the work of Hugo FANO because I was working with George Schultz toward my for my PhD thesis, trying to find as many electron resonances as I could in electron scattering cross-sections. Of course, because at this time there was some competition with a few laboratories, including NBS, where FANO had shown how to look for these transient negative ion states. So, as you all know, when an electron strikes a molecule or scatters from a molecule or an atom, it can at certain energy occupy for a time which is much larger than the usual scattering time, an unfilled orbital of the target. And you have a single particle if it just does that, and you have a two-particle, one-hole state if it involves electronic excitation. This is also called a core-excited resonance or Feshbach resonance. It's also Feshbach resonance. I'm not going to go through the whole FANO theory again, but it's always the same thing. Here we have, right? This is just a transient an ion, so it's an ion who lies in its ionization continuum. So when the electron takes off in the cross-section where you're looking at the resonance phenomena, it produces a FANO profile. And how can we see that? Well, what I found doing my PhD was the best way to do that was just to look at the attenuation of an electron beam going through a gas. And this is out of my PhD thesis, actually. It was argon in this example. And the trick was to find this cross-section when you look at the unscattered portion of the electron beam, actually to take the to use lock-in techniques to look at the derivative of the transmitted current. And like that, we were able to find many electron resonances. So you can see here, these are actually the first energy derivative of FANO profiles in the total scattering cross-section of argon. And what you see is the first resonance here associated with the first excited state. And the other ones are associated with higher excited states of argon. These are all core-excited resonances. So therefore, they are an electron bound to the positive electron affinity of an excited state. By the way, these are Vignes cusps. No, this has not brought too much attention, but it's still a type of feature that you can find in the elastic cross-section. Of course, the total scattering cross-section is really governed by the elastic. So when you do a transmission experiment in the gas phase, especially because of the exponential factor in the attenuation, you essentially see the elastic, the total elastic scattering cross-section. So this is the gas phase experiment. You just have a cell, and you look at the unscattered part of the electron beam, and you have this expression, so it's very simple. And this is the density and the length of the chamber. So in George's lab, having found many FANO resonances with this technique, I thought it would be nice to look in the solid phase to see if there were any resonances. And So I look at the mathematics of the problem, and in fact, if you freeze some gas on a metal substrate and coming with an electron beam of intensity I0 here, and you assume that you have a number of targets which are scattering the electron beam, you get an expression which is very similar than in the gas phase. Here you're in the condensed phase, you're doing that in ultra-high vacuum, and it's a very clean substrate. And because in this case there is a part of the beam which is a scattered part of the beam which is going to get to the metal substrate, you cannot do the pure transmission experiment. You get this additional factor in the denominator, but that's okay. It only would further enhance the effect of electron resonances, so that's very nice. So we have an equivalent, more or less, experiment, and let's go and try to find out all about these resonances in the condensed phase. At least that's what I thought would happen. Now, when I did if you look at transmitted current, I'm giving an example here with nitrogen. So this is nitrogen gas, and this is the solid nitrogen with about the same number of molecule attenuating the beam. Of course, you can the attenuation factor is NQLs, but the L, which is the thickness of the film, is very small in the condensed phase, but the density is very high, so it sort of compensates, and you have conditions which are similar. But this is transmitted current through nitrogen as a function of electron energy. You look in the gas phase, and in the solid phase, it's completely different. This is the doublet pi G state of N2 minus, the first electron occupying the first unfilled orbital. And this is, at the time, I had no idea what it was, but there was certainly a lot of structure there. Okay, so I said maybe because we don't have enough sensitivity, but we're going to use the derivative technique. And so I'm showing you some of the results here in the gas phase. In nitrogen gas, and in fact, beyond 7 eV, you see a series of core-excited resonances, and just lots of them. And these are vibrational series. They're vibrational level of negative ion states in nitrogen gas. And starting here, you have other very sharp features which are associated with the Rydberg states of nitrogen. And there is some other at higher energy. So I said, now we're going to do the condensed phase and take the energy derivative to get lots of sensitivity. So great. We have lots of structure. From 0 to 13 eV, I even took the second energy derivative to make sure that anything that was sharp would come out. And you have this tremendous amount of structure. Starting at the excited state, the features here are not electron resonances. They turned out to be threshold effect for electronic excitation. And below here, where the expression that I've shown would work very well, there is all kinds of structure that has nothing to do with electron resonances. So I said, maybe I made a mistake. It's just there's no electron resonances in the condensed phase. And I did all this work for nothing, because I didn't just do nitrogen. I did about 20 different molecules. And they all showed there was no electron resonances. Okay, I said, maybe this makes sense. Because your incoming electron, when you have a molecule and you're shooting an electron with a well-defined wave vector, this wave vector will have to change quite a bit, because you want to localize your electron on a molecule, so your delta X will get very small, but your delta K will get very large. And here the electron has a choice, because it gets into a solid, and there are all kinds of other well-defined wave vector in the which are vectors which are defined by the crystal lattice. And maybe it just scatters, exchange momentum with the lattice, and just continue to transmit through the lattice with well-defined wave vectors, so there's no localization of the electron at specific points in the lattice. So, okay, so it makes sense. Quantum mechanics agrees with that, and maybe I have to do something else and really go back to treatment planning. This was done in the Faculty of Medicine, you see. Because I wanted to understand the effect of radiation. by doing this. So I didn't get completely discouraged, and I now use a more refined techniques using electron spectrometer. So this time, again, this is a manipulator with a metal substrate here. Here we freeze, again, a gas to make it a molecular solid. It could be nitrogen again, let's say. And then we come in with a very monochromatic electron beam. And with a similar device here, we measure the energy of the electrons which come out of the film. So it's the inelastic, we can measure inelastic scattering electron. So when we look here, as a function of electron energy, at the elastic peak, and try to look for resonances, we still didn't find anything. However, if we look at energy loss as a function of electron energy, so we tune the monochromator to a given energy loss. So this experiment was again done with nitrogen. This time I had 0.1 layer of nitrogen sitting on a film. Let's see, we can choose just this one here. A film of, let's say, 32 layers of argon. And you tune the analyzer to measure the energy loss to 1 vibrational quanta of nitrogen. And then you scan the electron energy, and you see, you start, the cross-section here is very small. Around 4 eV here, it's still pretty small, but then goes up by at least an order or two of magnitude, and shows these features here, and this vibrational structure, which is characteristic of the doublet pi G state of N2 minus. And this is the gas phase, and you can see that it's exactly the same vibrational structure. The energy is different, and that's because of the induced polarization energy of the negative ion in the argon surface. Now, you can do that for pure nitrogen. You can do that for many types of molecule. And if you look in the inelastic channel, you will see very easily the resonance. And they're very strong in the inelastic channel. So they're certainly there. The electron localizes on specific sites, and resonances do, in fact, exist in the condensed phase, certainly in molecular solids. So I came to FANO with this problem. I said, well, how come they only exist in the inelastic channel? So I still remember I was sitting in his office with Mitio, and it took him about 10 minutes to provide the following answer. It's just that when you have the electron multiply scattered in a film, then if it's purely elastic and it doesn't produce a resonance. But then, and the reason for that is that when you create the negative ion state, of course, you polarize the atom or the molecule around, and the positive part of the induced dipole are attracted toward the negative charge, and there is motion of the lattice, so the lattice collapses around the negative ion. Of course, after the lifetime, after some time, the electron takes off, and necessarily there is no time of the lattice to respond to such a fast transition, and you dump energy in the lattice. So you cannot simply observe electron resonances in the elastic scattering cross-section. So then out of some conversation with Doug Mills, conversation of FANO and Doug Mills, Mills came with an explanation, a theoretical explanation, and calculated, formulated what would be the total probability to excite phonons. This is M is the number of phonons with an energy loss between, let's say, E and delta E. And these can be expressed in terms of here the lifetime of the negative ion, the dielectric constant of the system, and the Debye frequency. This is called a pseudo Debye-Waller factor because it includes a lifetime. Okay, so now that we know where to look, you can use again the electron energy loss spectrometer and say, so you cannot get it too accurately with the theory, but you know about where to look. And if you set your electron spectrometer to look at electrons that have lost 750 millivolt in an argon film, and here it's 12-layer thick, you will effectively, if you scan the electron energy, find the first core-excited resonance in solid argon. And this is this peak here. This is a little special. The state is an argon minus state, but it's in a solid, so it's actually an electron-exciton complex. So it's a charge that moves with electronic excitation in the argon. And we've done that at different angle of incidence just to show that the feature doesn't move in energy and that it's not, it's a localized state. It doesn't depend on the lattice parameters. Okay, so this is clearly not in the elastic cross-section, and you can see it very well here from the energy loss spectra in the same layer of argon. Okay, so again, we're looking at the electron being promoted from a p level to an s level, the 4s level. So the state is 4s squared in the outer orbital, 2 excited electron, and with the score here. So we look here again with this time is different. We come in on the argon multilayer with a specific electron energy from the electron monochromator, let's say 11.45 eV, and we simply look at the elastic peak. And you have a sharp peak at 0 eV and nothing else because there's no state to excite, right? Except phonons. So there is an asymmetry here, which is due to multiple scattering of the electron in the film and producing phonon excitation. And if you blow that up by a factor of 200, you see the tail, the photon tail here that can extend up to about 1 electron volt energy loss. But you can do that for any energy. You're always going to see that, except at the resonance energy. At 11.75 eV, you see a peak appearing here, which is due to the extra energy supplied to the lattice due to the formation of an argon minus state. And this is the theory of Mills from the calculation. Okay, so in this talk, I could just go on and show you FANO line shapes. But you've already seen a lot of FANO line shapes. So they would all be peaks in cross-sections and so on. And I can guarantee you, you should believe me, that now electron resonances are as prominent as what we've seen here with photons. It's been very surprising to me that in the last 30 years, when I started my PhD thesis, actually, we only knew about a few rare gases, a few cases like the rare gases and a few molecules where there were electron resonances. And today, I think they're just in anywhere. They're on Physisorb system, Chemisorb system. They're in molecular solids. They are, of course, in any gas. And I think you could name me a system, and I'll find you a resonance, or even more than a resonance. And maybe you don't believe me, or you want to try a real tough one on me. And you would say, well, if you think you can do that, why don't you try the DNA molecule? Okay. DNA is a very long, indeed, molecule, and here we're getting to the biology. And it's made of a sugar phosphate backbone, two strand made of sugar phosphates. So these are repeated units of carbon and phosphate here in oxygen, and a tetrahydrofuran molecule, a ring, if you like. And this ring is chemically linked to the bases. As you know, there are 4 of these bases. And the bases are linked together by hydrogen bonding. And this holds the 2 strands of DNA together. And as you know, the genetic code depends on the position of the bases. So we wanted to look at the breakage of these strands. Because that's going to be very important for radiation damage. As you probably know, high energy radiation produces essentially low energy electrons and ions, and most of the energy goes into the secondary low energy electrons, and the energy of these electrons lies below 10 eV. I mean, most of them are found below, let's say, 20 eV, like 85% of the low energy electrons. So it was very important to know if yes or no, these electrons could actually break strands of DNA, particularly double-strand breaks, because this would be very dangerous. As you know, the cell, we can lose the genetic information in this case and produce mutation in cells. So this is the link to radiobiological physics and radiotherapy. And here is what we found. It was even more than I expected, actually. If you look at per 10,000 electron, if you look at the number of single-strand breaks and double-strand breaks in DNA, it shows this feature as a function of electron energy. And here we have a number of resonances which are making this peak. And what is even more obvious is in the double-strand break, we obviously have a number of electron resonances, again, which can be identified. Well, they cannot be specified, but we know that this is a signature of electron resonances. So you see these profiles of resonances here are giving us very important information. Now, what is very surprising in this result is that these 2 points here, and you know, the error on this point is small. We have 6 measurements per point, are at 0, at the 0 baseline, which means that below 15 eV, it's only electron resonances that break DNA. And that must be important because most of the secondary electrons have energy below 15 eV. So it may be that electron resonances actually are playing a dominant role in the effect of radiation in biological cells. So we went on to study that. That would certainly be a question I would ask to FANO if we're still here. Why is it like that? That's not obvious. So we went on to study in detail and to look if there is not, because we have a peak in the double-strand break at 10 eV, if we see anything at that energy. So we decided to look at the various constituents of DNA separately, because obviously this is a very big molecule, but if you want to break something, you must localize your electron. It's again this question of localization in a volume which is of the order of the size of a tetrahydrofuran ring or a DNA base. The wavelength has to be of that order. So also, you must create a core-excited resonance, which means that you need an excitation energy of the order of 10 eV, so that has to be small again. So it's all the same thing, but it leads us to look at specific components. And in the case of this is the backbone, so we started to look, for example, at the tetrahydrofuran ring here to see if the electron localization was not there. Actually, we look at many places, but I'm showing you the best results here. And and we also look at the longer, at the same molecule with a chain on it, so as to mimic the rest of the molecule. And if we look in the dissociative electron attachment channel, this is what we find. You see? Here we are looking, we have the film of tetrahydrofuran and the 2 other derivatives, 10 layers in ultra-vacuum, and we have a mass spectrometer where we look at H- production as a function of electron energy, and it produces a peak here around just 10 eV where we see the double-strand break. That makes a lot of sense. This is part of the backbone. And so what's happening here, we're producing tetrahydrofuran minus that then dissociates into H- and a corresponding radical. And so it seems to fit very well. And in fact, the interesting thing is if you increase the chain of the backbone, you don't get much of a change. So it seems the electron is really localized on the tetrahydrofuran ring. So we're getting very specific here on how radiation is actually changing DNA. And out of that, we have some very new results, which unfortunately I don't have time to present, but where we are modifying the DNA with radiosynthesizers, with molecules which we believe now are going to change the effect of radiation in cells. And we have worked with known radiosynthesizer, and we can specify the mechanism of radiation action. And to show you that we can do that is because looking at these profiles, we can actually do almost the early organic chemistry, if you like, of the process. For example, if we look at electron scattering on a base of DNA, now this also has resonances in the region starting from 8 to about 15 eV. So this could be more responsible for the single strand break, but also maybe the double strand break also. We're not exactly sure what's going on. One of the major reactions is electron attack at this position here. So here you can have, depending on the base, you could have a hydrogen or a CH3. And you will get a hydrogen minus or CH2 minus, CH2 minus, and so on. So I'm just trying to make a story short here without showing the data itself. But we also measured not only the negative ions coming out, but the neutral as a function of electron energy. And in both cases, we see the same electron resonance. So, and on top of that, we find that the OCN and the CN products have the same and keep the same relative intensity as a function of electron energy. So it must be a common precursor, which is here, which is HOCN. So we put this on one side of this equation, this on the other, and we know the intermediate species. And we talked, this is a lactam. To me, it looks pretty weird. But the organic chemists tell me this is perfectly okay. This molecule can be made. So we're even with these line shapes and FANO profile, we actually can start doing almost organic chemistry on a time scale. All these things occur on the femtosecond time scale when you are irradiating organic or biological molecules. How much time do I have left? It's okay. Okay, so so we also look at quite a number of molecules, and one of them is the dimethyl disulfide, because this is a bridge in the proteins, and this is what if you break this bridge, you break the function of the protein is going to change, and so we look at this. And just to tell you how prominent resonances are in the system, again, this is all what we found. We found that this single state of the negative ion around, this is, well, these states are formed between 4 and about 12 eV in this compound, in dimethyl disulfide. And we found that the decay channels are very numerous. And so electron resonances give all kinds of primary products in proteins. And we also found that compared to other components of the protein, this type of resonance creates, well, I should say that the sensitivity to low energy electrons of this disulfide bond is about 100 times larger than for other parts of the protein. So protein function must be extremely sensitive to radiation based on that. I'm going to come back to something more fundamental, and then I'll finish. This is the water molecule. It's amorphous, condensed at 27 K, made, I mean, from condensation of water at 27 K, and raised at different temperatures. So we studied the temperature, the yield of D minus from D2O ice as a function of energy and temperature. And we also, well, there are all kinds of reasons why it increases here. I'm not going to go through that, but you see a maximum around 8 eV, which is again forming D2O minus, dissociating into D minus and OH. But the DNA molecule is held together in a structure by some water, which is called a structural water. And that would also, this means here that we would produce a lot of OH also, which is very detrimental to the DNA and can produce further reactions. But then I will leave you with something fundamental, which brings me back to what I said in the beginning of the talk to show you that everything is connected with physics. This is, again, dissociative electron attachment in water. So you have H minus production, measured with a mass spectrometer. But this from water, but only 0.1 monolayer, you see, of H2O has been this time deposited on a 20 layer of krypton. And so you see the usual dissociative electron attachment profile, which is due to the formation of a doublet B2 state of H2O minus, dissociating into H minus and OH. But on krypton, you see a peak here, which appears about 0.5 eV below the first exciton state. And this peak comes from the krypton, of course. It's because you form krypton minus at this energy. So you form an electron exciton complex in the substrate, because now the substrate is krypton. This object moves around, and then when it finds on the surface a water molecule, it exchanges both its charge and energy, and then forms the H2O minus state, which is actually an excited state of the negative ion that then dissociates. Now you will say, if this is true, then I should be able to change the krypton from another rare gas with xenon here, and I should find the peak again, but at the different energy, of course, because the excited state in xenon is at lower energy, and exactly this is what happened. You see a very sharp peak here due to the electron exciton complex formation in xenon minus. So you can see that in the condensed phase, these negative ion states would couple together, and I could go on and show you all kinds of interesting things we can do with these. Well, thank you very much for listening. It's been a pleasure.